In my last video, I introduced set identities. Now let's use those to try to prove some new relationships. So right here we have the complement of the union of three sets, A, B, and C, and we want to show that that's equal to the intersection of the complements of each of the three original sets. Now you may look at that and think, well, isn't that basically De Morgan's? And you'd be right. Recall that De Morgan's, for those that don't recognize it, De Morgan's law for sets would have two sets involved. The union of A and B, and then you take the complement of that, is equal to the complement of A intersected with the complement of B. Okay? Now this is for two sets, this is for three sets. Now you may also look at it and think, well, if it works for two, doesn't that mean we automatically know it works for three or four or five? Well, not necessarily. This has been shown to be true specifically for two, and now we're going to extend it to this by using set identities. Okay, but we don't necessarily automatically know. We may have an idea, but that's not the same thing as proving it. So now let's demonstrate that it really is true, and then you could extend this idea to others. So how are we going to do it? Well, remember that we also have the associative property. Okay, for unions, it says that if I have the union of A and B and C, then I can group these to say that the union of A and B, which is some set, right? It might be the empty set, but it's still some set. And then you could take the union of that with C is equal to the union of B and C, and then take the union of that with A. Okay? So by doing that then, and I'm going to use square brackets to try to make it a little more clear, I'm going to group A and B into one set, right, by having the union of them, and then whatever set this is, for example, it might be D, we can find the union of that with C, and then take a complement of that. So this is a set, and this is a set, so now we have two sets. So now I can use De Morgan's. So when I do that, I'll have this set, which we can't break down anymore at this moment, the set that we get from finding the union of A and B, the complement of that, and now the intersection of that with the complement of C. And now we can take the left one and apply De Morgan's to that to get the complement of A intersected with the complement of B intersected with the complement of C. And that's what we're intended to show. All right. Now, if you'd want to, you could have been more anal about it, and we could have kept the parentheses here for the moment, and then said, well, we don't really need the parentheses since this is an intersection, this intersection, and then finally just do this. But either way, it's the same relationship. All right. Now let's look at this one. A minus B is equal to the intersection of A and B. Now recall that the difference between sets, A minus B, can be written as the intersection of A and not B. And recall that A minus B, if we draw a Venn diagram here, this is B, this is A, we subtract out this part over here, so we're left at this part of A. That is, we remove the intersection of A with B from A. All right. So I'm going to use that here. So this will give me A minus, and then we have the intersection of A with not B. And now what do we do? If I were to think of this as being a set, which it will be, once again, it might be the empty set, but there's going to be some set, this intersection here. If it were C, for example, so let, C equal the intersection of A and B, well then we would have A minus C, and I can do the same thing I did before. Well, this then becomes the intersection of A and not C. So I'll use that idea right here. So this will be the intersection of A and not this set. Or excuse me, the complement of it. It's not logic. Right? So there's the idea. And now I'm going to extend this into here using De Morgan's. And so this became the complement of A union complement of the complement of B. So what's that? Well, if we think over here, if this is S, the universe of discourse, and this is B, well then this would be not B. That is everything that's not in B, but that's part of the universe of discourse. So the complement of this has to be back to B. It's like in logic where you have the negative of the negative. You get back to whatever you started with. So intersection, union, I have a distributive property I can use here. And so what's the intersection of A and its complement? Well, that'd be the part that overlaps. And so just like looking here, if everything outside of B is the complement of B, if I try to look at the intersection of the two, I get the empty set. And so I have union of A and this right here. Or sorry, there was none here. We got rid of the complement, so that's not there. And now what's the union of the empty set with something else? Well, by using the union, I'm combining everything here with everything here and removing any duplicate members. Well, this has nothing, so we add nothing to this, so it ultimately becomes just this right here, which is what we wanted to have. Let's look at a couple more. Now I want to show this relationship here is equal to the empty set. Now here we have B union this expression here, union A, and then the complement of all that. Now we can use what we just showed before. One of the reasons you do things like this is you expand the list of things that you know are true based upon what we started with. And so now that I've extended De Morgan's to 3 sets, I can use that right here. So this becomes a complement of B intersected with AUB complement, right? Because this complement goes in on this, intersected with complement of A. Just like before, the complement of the complement just gives you the A union B, so this becomes a complement of B intersected with A union B, intersected with the complement of A. And now I can group these, so this is a set intersected with a set, intersected with a set. I can subgroup it using the associative property. Now I can use a distributive property. So the complement of B intersected with A, I can't simplify that anymore at the moment. And the union of that with this, well, this is the intersection of the complement of B with B, which we already know is the empty set. We saw that before as well. Now I'm going to take the union of the empty set with this, which will just be this. I can drop the parentheses, or actually I'm going to regroup. So now instead of the intersection of this intersected with this, I'm going to shift the intersection and have the complement of B intersected with A intersection with the complement of A. The intersection of A with its complement is the empty set. And now the intersection of the empty set with the complement of B is they don't have any overlap. They can't because this is the empty set. So they share no members. So it ultimately reduces to this. And that's what we were trying to get right here. So we did that. Let's look at one last one. So now we'll have the union of B with this expression with the complement of A, and we'll show all this together is the universe of discourse, which we write as S. So I'm going to use the distributive property. Or first I'm going to regroup to make it more clear. Now the distributive property. So can't do anything with this at the moment. Look at this. The union of B with its complement is everything, right? Because if we think about it, if this was S, and let's say S contained 1, 2, 3, and 4, and that B was the 1, 2, 3, and then 4 would be the complement of B, right? Well, if we talk about combining everything in B with everything that's not in B, that has to be all of S. So that's what we get here. So this becomes, once again, B union with A, intersected with S, and then union of that with the complement of A. Now what is, we have this right here, I'm going to use the distributive property. So B intersected with S, union, A intersected with S, and then union, sorry, it's just U, complement of A. And if I say, what's the intersection of B with S, going back and look at this right here, well, if everything is S, and we talk about where they overlap, and B is a subset of S, well, their intersection is just B. And so this becomes B union, same logic here. If A is a subset of S, then the overlap there is just A. And now I have B union with A, all that union with the complement of A. So I can reorganize using the associative property. A union with what's not in A, well, that's the entire universe of discourse. So this becomes B union S. And once again, if I combine everything in S with what's in B, well, B is already a subset of S. So this reduces to S. And that's what we wanted to produce right here. So hopefully you have some idea how to go about showing these things and expanding your knowledge instead of just looking at something and hoping that you know if it's right or wrong. You can attempt, in some cases, to use Venn diagrams to answer certain questions. And I didn't really use any for these. But the problem you get is in some cases, there's so many different possibilities. You know, because you're talking about, well, maybe this is A, and this is B, and this is C, where they're completely disjoint. But then you might have a case, if you're talking about, say, where they intersect. For example, what's this? Well, you might have this. Or you might have A and B overlap, and then here you have C, or you can have A and C overlap, and B is disjoint from them, or B and C overlap, and A is disjoint from them, or all three overlap, something like this. So you have all these possibilities, and it just becomes, in many cases, too challenging to try to resolve what happens when you do certain things if you look only at Venn diagrams. But they are useful to give you an idea of what's going on, and there are some cases where you can look at them and understand really what the relationship means. But there's cases where you really need to understand how to use the set identities to manipulate relationships into something that you finally can settle on like this. And in that sense, it's kind of like properties of real numbers. We use the associative property and the commutative property and the distributive property and other things for real numbers to simplify expressions. So that's what I've done here.